All right, I want to look at these power tables a little more and give some terminology, and we start to notice some patterns, right? So again, these are the number in the top left corner is the mod, and the columns are the elements of the units mod m, right? It's everything for primes, everything non-zero. But for something like 15, it's just these numbers because those are the numbers relatively prime to 15. And then the entry in column A, row N is A to the N mod M. So, right, you're just like, these are like the powers of 7, mod 11. Okay. The thing I want to notice is the first thing I want to notice is if you start with anything, like start with, I don't know, the powers of 4 mod 13, right? So you multiply, 4 to the 0 is 1, times 4 is 4, times 4 is 16, which is 3 mod 13. Then you get 12, 9, 10, and then you get to 1 at this moment, the sixth power. So we can say something like, I don't know, just to tease this out, like 4 to the 6th is 1. Is congruent to 1 mod 13, or is 1 in U13. But no earlier power of 4 is 1. Right? That's the first time it happens. Right. We know everything cycles back to 1 eventually, especially since we've proved this sort of Fermat theorem or its generalization. We know we're always going to get back to 1 eventually. You can actually even show that in a more elementary argument, almost like a pigeonhole principle type argument, that you're going to get back to 1 eventually just by taking powers of a number. But here it happens at powers at the exponent 6. That's the first time you get 4 gets back to 1. And so we're going to give that a name. That's going to be called the order of 4. We'll say the order of 4 equals 6. So let me just go write down a definition here. So, or maybe I'll just actually let me move this down a little bit, give us some more room, and then so I can say, we'll say the order of 4 in U13 is 6. And sometimes I can write that a little better. And we'll want a notation for that. The notation will be, we can say the order of 4 equals 6, or sometimes people just use like an absolute value thing. Of course, you need to know the context that we're talking about, that this is all in U13. Because like, if you look at the order of 4 in U11, right, the order of 4 is 5 in U11. So, you need to know the mod that you're in. So just to be a little more formal at the definition, so I give you a definition of order. So given A living inside the units mod M, we say A has order N if the following 3 conditions, right? So N should be a positive integer. That's important. Everything to the 0 power is 1. Right up here, everything to the 0th power is 1, but we don't want to think of that as the order. That doesn't tell us any information. So N is a positive integer. 2, A to the N equals 1 in U sub M. And 3, we want it to be the first time. So A to the I is not equal to 1 for 1 is less than or equal to I is less than M. sorry, n. Right? So this is like the first time. The first time the powers of A cycle back to 1. Powers of A cycle back to 1. We know they always end up back at 1 eventually, right? But this is the first time it happens. So that's the definition of order. Okay. And so for just as examples, you know, look at these tables, like in U22, say, 9 has order 5. So that's the first time that the powers of 9 get back to 1, is at 9 to the 5th power, right? 9 to the first power is not 1, 9 to the second power is not 1, 9 to the third power is not 1, 9 to the fourth power is not 1, but 9 to the 5th power is 1. So that's the order. We write, like I said above, we write the order of A equals n, or just the absolute value of A equals n, like that. Those are two typical notations. Okay, so that's just the term order. It's an important term. It's going to come up a lot. We'll talk about the order of elements all over the place for the rest of the semester. It's going to come up a lot. The other thing to notice is that the pattern to notice is that sometimes the order is as big as it can possibly be, right? Like in 17, mod 17, we always know we return to 1 at the 16th power. That's for Mausel theorem. But sometimes, like for 5, that's the first time it happens. For 6, that's the first time it happens. For 9, it's not the first time it happens, right? It returns to 1 at the 8th power. So when we have something like that where it actually doesn't get back until the last possible moment. Okay, let me look at this table. The other thing we can say is, like, for something like 5, the powers, well, what they really do is they cycle through every single element of U17, right? We get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This is fun. 12, 13, 14, 15, and 16. Okay, so like there's another thing there. It's like the powers cycle through every element of UM. So so another definition. If A in UM has order phi of M, right? That's the number of elements of the whole set. Then A is called a generator. Or a primitive root. There's this more archaic term, primitive root, for U sub M. Handwriting is just really atrocious sometimes. For U sub M. Okay, that's terminology. It's basically just saying, right, that this thing generates. I mean, it's called a generator because it generates everything. The powers of A generate all the elements of U sub M. Another way you could say is it cycles through. The powers of A cycle through all the elements. Powers of A. This is, it's almost problem with using A is it looks like the article A, not the variable A. So we could also say the powers of A cycle through all the elements of U sub M before returning to 1. Right, and so just as an example, in U sub 22, say, right, we have the generators are 7, 13, 17, and 19. So e.g. in U22, the generators are, I already forgot the numbers I said, 7, 13, 17, and 19. I said cycle through right here because that's another terminology. So if U sub M has a generator, we say U sub M is cyclic. That's another terminology. These are all definitions, I guess. That's the term. So it's called a cyclic group. Okay. So we'll notice if you look back at the power tables, all the data, but especially up here, notice that 11, 13, 17, those are all cyclic. U11 is cyclic. You know, here's some generators. U13 is cyclic. U17 is cyclic. U22 is cyclic. U15 is not cyclic. If you look at this table, there's no column that generates all of these numbers before getting back to 1. In fact, the fourth power of everything is 1. So in our examples above, so we see that U11, U13, U17, U22 are cyclic, but U15 is not. And so there's kind of a big theorem, which takes really some effort to prove, but it's kind of a nice theorem that we'll try to prove over the course of the semester. For P prime, UP is cyclic. So there are always generators. And this is going to be useful. We're going to use these powers a lot in cryptography. This is a better mixing effect than even just multiplying like by a fixed number, right? Like if I multiply everything by 3 mod 11, that mixes up the elements 1 through 10. But taking the powers of a number even gives you a stronger mixing, and especially for larger numbers. And so we're gonna want to have generators. So that's why primes are very important, because it turns out that UP is always cyclic. 22 happened to be cyclic also, but even though 22 is not prime, here it turns out that anytime you have a product, if M has at least 2 different odd primes in it, so it turns out that's not cyclic. So also if M contains 2 distinct odd primes, meaning in the factorization, this is a little bit easier to show. U sub M is not cyclic. So U sub 15 was not cyclic. U sub 30 is not cyclic. U sub 35 is not cyclic. That's 5 times 7. Yeah. And so that's some stuff. I mean, if you want to classify completely, you can. It turns out that twice a prime is cyclic. That's 22 as an example. Turns out that prime powers are always cyclic. Like if you look at, you know, U9 or U27 or U25, those are cyclic. And twice prime powers are cyclic, and that's it. But that, again, that's actually a big theorem that actually probably we won't even prove because it would take a substantial amount of effort. Okay, so that's just some of the terminology and stuff. What we want to do is actually there's different properties we can prove about order, and we're gonna do some of that next. But I will stop. Should I stop now? You want me to stop? Yes, I'll stop.